In this second session this week, we will focus specifically on the challenges of applying deep learning to medical imaging data, predominantly looking at strategies for mitigating or compensating for this so as to deliver impactful medical AI applications. The biggest challenge with medical data, taking imaging as a specific example, is its sheer complexity. One might have no problems pointing out an aeroplane or a penguin, but can anyone tell me which objects in this CT image represent the liver, spleen, or kidneys? Let alone decide whether they're healthy or diseased. In this example, one of these images represents a brain scan of an infant who went on to be diagnosed with autism at 4 years old. Can you tell which it is? Interpretation and classification of medical images takes years of specialist training, and even then the signs of disease can be very subtle and occur across a backdrop of significant natural variability. If we as humans struggle to read these images, then how does one go about teaching a machine to do it? To bottle up all those years of medical professional experience, building in contextual information and accounting for confounds, this can be far from straightforward. The second significant problem with medical data is size. The individual images are very big, often three-dimensional with image grids sampled hundreds of times on each axis. Biometric or genetic data is enormous. Our recent neonatal genetic dataset contains 4 million data points, and that is only sampling at a fraction of locations on the genome. Add to that the vast amount of personal information stored in electronic health records, and we are presented with significant challenges in terms of compute power. At the same time, in terms of numbers of samples, some of these datasets are very small. This is a particular problem for medical images, which are expensive to acquire. With the exception of UK Biobank and a handful of others, dataset sizes tend to number in the hundreds or thousands. Even Biobank is tens of thousands of complex, high-dimensional 3D images, whereas ImageNet contains 14 million hand-labelled 2D images. For natural images, labelling is cheap to obtain because, as we've already seen, anyone can label an easily recognisable object in a photo. Biobank, on the other hand, comes with thousands of noisy labels, for example of subjective measures of IQ and mental health, and heterogeneous medical diagnoses confounded by variables such as age and sex. All of this is a problem because, as we've already seen, machine learning typically needs more examples than parameters to avoid overfitting. We therefore face a trade-off between expressivity and generalizability of our models. Indeed, there have been a few papers suggesting that traditional ML methods typically outperform naive implementations of deep learning. And finally, there's an issue of ethics and heterogeneity. So when it comes to medical diagnoses or prognoses, the consequences of a wrong answer can be profound. At the same time, data use is rightly protected by GDPR, so it's quite a challenge to openly release medical data without taking strong precautions to safeguard the subjects from being identified. At the same time, medical data shows significant confound variation. So, for example, in the instance of the brain, everyone's brain will look very differently, even if they're all healthy. And so this confounds the signal, as you must consider what is normal for this specific individual and account for a range of symptoms and presentations of different types of disease. On top of that, the same object may look completely different, acquired with different acquisition schemes. It might even vary for the exact same protocol, but on different scanners. So deep learning for medical imaging is far from straightforward, which is why we need a bespoke course dedicated just to tailoring the technique to medical data, and even then we'll be mostly focused on medical image analysis. In this week, we're going to review the fundamentals, how to pre-process and adapt generic networks to train successfully on medical data. We will look at the importance of careful pre-processing, techniques for intensity normalization, use of weight decay to regularize and reduce numbers of learnt parameters. We'll also look at how to simulate the appearance of much larger datasets through augmentation and investigate alternatives to batch normalization with variants which work much better when you're constrained by memory to a batch size of only 1 or 2 samples at a time. After that, the rest of the course continues to be focused on strategies to make the most of small and complex imaging datasets, including network visualization techniques and use of uncertainty to try and get explanations for what the network is learning and where it is confident in its predictions. We'll also look at transfer or multitask learning to address small dataset sizes by pre-training on larger datasets, or to support training a model on multiple different scanners from multiple different sites. And finally, we'll also look at semi-supervised or unsupervised learning, which will address or partly address the problem of not having very many annotated datasets.